So in the last lesson, we learned about graphing rational functions. Today, we're going to extend that knowledge of graphing rational functions. In the last lesson, we learned how to find the vertical and the horizontal asymptotes. Vertical asymptotes are going to occur when your denominator is 0. Your horizontal asymptotes are going to occur if you have an equal numerator with the denominator. That is when you're going to have a horizontal asymptote, and that is going to be whatever your coefficient of your numerator divided by the coefficient of your denominator is going to be. If your numerator degree is greater than your denominator, you have no horizontal asymptote. And today we're going to extend our knowledge of graphing by looking at some other possibilities. Oblique asymptotes are located at angles other than a horizontal or a vertical. So these would be angles where we have a line that is slanted. It's not horizontal, it's not vertical, it's at some sort of angle. That is what we call an oblique asymptote. Oblique asymptotes occur when the degree of the numerator is just one more than the degree of the denominator. So if we were to take the numerator and divide by the denominator, we would get something like y equals mx plus b. We would get a linear equation upon doing that, and that linear equation is going to be the equation of our asymptote, that is the oblique asymptote. So it is going to be occurring at an angle. It does not really matter what your remainder is. So after you do your division, you're just looking at the slope-intercept equation regardless of any type of remainder after you've done your division. So as an example, x to the fourth plus 3x cubed all over x cubed minus 1. My degree of my numerator is just one more than the degree of my denominator. And therefore, we will have an oblique asymptote. When I do that division, either through synthetic division or by long division, I'm going to get y is equal to x plus 3. And so I have an oblique asymptote where the equation of y equals x plus 3. If I were to draw that line using a dashed line, then that would tell me where my oblique asymptote is going to be located. So what are the asymptotes of x squared plus 4x plus 4 over 2x minus 1? So let's start off by looking at my vertical asymptote. My vertical asymptote is based off of my denominator being to 0. So I have 2x minus 1, and when I set that equal to 0, I get x is equal to a positive 1/2. So I have a vertical asymptote at 1/2. Horizontal, my degree of my numerator is greater than the degree of my denominator, so I have no horizontal asymptote. However, the degree difference is only that of 1. So I could have an oblique asymptote. How do I find that oblique asymptote? Well, I'm going to divide the numerator by the denominator. When I do that, again, either using synthetic division, which I could in this case, or long division. If you need a reminder on how to do that, go back to section 5.2. That's where we covered long division. Synthetic division was shortly thereafter. But when we work that out, we get x is equal to 1/2 x plus 2 1/4. So I have an oblique asymptote at y equals 1/2 x plus 2 1/4. So I've got my vertical asymptote at 1/2, and then I've got an oblique asymptote that crosses my y-intercept at 2.25 and has a slope of positive 1/2. We find the rest of these points on my graph just like we did yesterday, where we plug in some values for x and find the corresponding values for y. The nice thing about knowing where your oblique asymptotes are located is it does allow you to kind of double check your work as you're plugging in values for the x. You know you're not going to cross over those asymptotes. What are the asymptotes of x squared over x minus 2? I'll give you a moment, find the vertical, find if there's any horizontal, and then any oblique asymptotes, and come back and we'll see how well you did. So to begin with, let's look at the vertical. X cannot be equal to 2. That would put me at a 0 in my denominator, which would be a vertical asymptote. So x equals 2 is my vertical asymptote. For my horizontal asymptote, since the numerator is greater than the denominator, there is no horizontal, but I do have an oblique. So if I divide x squared by x minus 2, I end up getting an equation of y equals x plus 2. Again, we're not concerned about any remaining portion to my division problem, just the quotient piece itself. So x plus 2, that means when I draw my graph, I'm going to have a vertical asymptote at 2, and then there's going to be a oblique asymptote. It's going to cross my y-intercept at 2, and it's going to have a slope of 1. So graphing that, this is what it would look like. Again, we get the rest of our graph by plugging in values for x, finding the corresponding values for y using our original equation. What are the asymptotes for x cubed minus 1 over x squared minus 4? Go ahead and figure out what your asymptotes are, and we'll come back and see if you get the right answers. In my denominator, I have x squared minus 4. So that means x squared is equal to positive 4, which means x cannot be equal to positive 2 or negative 2. So I have two vertical asymptotes, one at plus 2, one at minus 2. Then if I do my horizontal asymptote, my degree of my numerator is greater than the degree of the denominator. So there is no horizontal asymptote. However, I do have an oblique asymptote. If I take x cubed minus 1 and divide by x squared minus 4, I get y is equal to x. So this one's going to go through the origin. I did put the plus 0 there just for emphasis sake. You don't have to have that. It is going to go through the origin. It's going to have a slope of 1. Now we can plug in values for x. Start graphing. I put my verticals, my two verticals at negative 2 and positive 2, and then my oblique asymptote right along here, and then I can plug in values. Now you will notice that my graph does cross over one of my asymptotes. It is important to note that when we're talking about oblique asymptotes, it is dealing with just the end behavior of our graph. So the end behaviors would be as we go toward negative infinity and as we go toward positive infinity on my x. It is not going to impact the middle behavior of my graphs. So I can actually have part of my graph cross over an asymptote. That brings us to the second part of our lesson, and that is discontinuity. If something is discontinuous, that means it has stopped. In our particular case, it has a hole in our graph. So some graphing may end up having holes or points that do not work in the graph because a point is undefined at that specific location. And that point is called a discontinuous point or some sort of discontinuity. If both the numerator and the denominator share a common factor that includes a variable, there is a point of discontinuity. Let me give you an example of this. If I were to factor a numerator, and let's say when I do that I get x plus 2 and x plus 1 as the two factors, and in my denominator I have an x plus 1. Well, I have a common factor for both the numerator and the denominator. Well, since they cancel out, that could indicate that I have a hole in my graph. So rather than it being a vertical asymptote, it may actually just be a hole. It's going to be discontinuous when x is equal to negative 1. If we look at the graph here, you will notice that the line does go straight through. However, there is a hole right here at x equals negative 1. So rather than it being a vertical asymptote, it is a hole. So it jumps over that particular point, and therefore it is discontinuous. This line does not continue throughout. It has a broken part to it. So let's try one of these. Let's say I have x squared minus 16 over x minus 4. As you're graphing these and preparing to graph, you still go through the same process. Do I have any asymptotes? Well, it's possible that I have an asymptote at x equals 4 because that is where my denominator is equal to 0. However, if it is also a factor in my numerator, then that means I could just have a hole at that location. So I'm going to need to factor my numerator now. If I factor my numerator, get x plus 4, x minus 4. Well, now you can notice that I have an x minus 4 in the numerator and in the denominator. Therefore, I am going to have a hole when I graph this particular problem. How is it going to look? Well, what is the piece that did not cancel out? It's an x plus 4. So that means if I graph x plus 4, I will get the graph of what I need with a discontinuity point at x equal to 4. So it's going to look something like this. It's basically the x plus 4, where I'm going through positive 4 on my y. I have a slope of 1. But I have a point of discontinuity there where x is equal to 4. Try x squared plus 4x minus 5 all over x plus 5. If you start by factoring the numerator, you get the factors of x plus 5, x minus 1. Notice once again that the x plus 5 is the same in both the numerator and the denominator. So when x is equal to negative 5, rather than having a vertical asymptote, I have a hole. A hole in my graph. My graph is going to be equal to that of y is equal to x minus 1 with that one discontinuous point. So graphing it gives me a graph that looks something like this, where I do have my x minus 1 as my line, but if you'll notice right down here, we have a point of discontinuity when x is equal to negative 5. Try graphing x cubed plus 2x squared minus 9x minus 18 over x squared minus 9. I will give you a little bit of a hint here. We have 4 terms in our numerator, which means we're probably going to be factoring by grouping, but make sure you look for a common factor first. Remember, that's always the first thing we look for. In my denominator, I have a binomial, so I'm going to look to factor out a common factor and then go with something maybe like a difference of squares. So go ahead and take some time, factor those out, come back, and we'll see if you got the right answer. So walking you through the process, since it has been a while, we are going to factor out of my first 2 terms an x squared, giving me x squared times x plus 2. Out of my last 2 terms, I'm going to factor out a negative 9, giving me x plus 2. In my denominator, I have a difference of squares, an x plus 3, x minus 3. Now, back to the numerator, I have a common factor of this x plus 2 piece, so I can factor that completely out, and that's going to give me x squared minus 9 over x plus 2. Well, that x squared minus 9 is an x plus 3, x minus 3. So my complete factorization of my original problem is x plus 3, x minus 3, x plus 2 over x plus 3, x minus 3. Now, in this part, we have 2 factors that are common to both the numerator and the denominator, which means I'm going to have 2 holes in my graph. My graph is going to be basically the line of y is equal to x plus 2, but I'm going to have a hole at x equals negative 3 and x equals positive 3. So upon graphing it, it will look something like this. We have the line of x plus 2, but we do have a point of discontinuity at negative 3 and at positive 3 on my graph. So, in today's lesson, we learned about oblique asymptotes. Oblique asymptotes occur when our numerator has a degree that's just one more than our denominator degree. We find the asymptote by dividing the numerator by the denominator. That's going to give us a linear equation. We don't care about the remainder portion. That linear equation I can draw as a oblique asymptote, keeping in mind that it only impacts the end behaviors of my graph, not middle behaviors. The second part that we learned is points of discontinuity. Discontinuity occurs when you have a common factor for both the numerator and the denominator. So if I have an x plus 3 in the numerator and an x plus 3 as a factor in the denominator, instead of having a vertical asymptote at that point, I'm going to have a point of discontinuity or a hole in my graph.